With magnetic force, this is just one simple application, which is magnetic force on a conductor. Pretty easy. It has its own formula, which is nice. Magnetic force, instead of being V, meaning the speed of the charged particle, now we're talking about electric current, right? Because it's some electron current through a conductor itself. Okay? And basically it just means exactly what I wrote down. If you place a current carrying conductor inside a magnetic field, it will feel a force. That is the motor principle. It's how motors work. And this is how you figure out the magnitude of that force. And, well, the direction, but we knew that already. Just a little thing, you know, because I'm using a computer. That's my doohickey, that's my L. See the little, how the font is? I just chose a weird font so that you could distinguish between I and L. Okay, so current times length times field strength times the angle. Okay, and whoa, another definition of Tesla. And again, chosen on purpose, the magnetic field strength. When you have 1 meter carrying 1 amp, feels a force of 1 newtons. Okay, again, what is it? It was made up. Tesla is just a thing that was made up because it's a convention that works with nice numbers, and it works. All right, let's use that equation. So we know a 1.8 meter long straight conductor experiences a maximum force of 1.8 newtons. That maximum should tell you something, what the angle is going to be. And it's rotating in a uniform magnetic field of 1.5 Tesla. Calculate the angle between the magnetic field and the current in the wire when the force is a maximum. You don't need to calculate that. Part A down here. No calculation required. 90 degrees. Okay? B, calculate the current and minimum force in the wire. So to calculate the current, we have to use, here's our data. Okay? We know it's 1.5, 1.8 for magnitude of force. We're given a 1.8 meter long wire. We know the angle's 90 because it's a maximum, and we're solving for current. Just sub in the numbers, 0.67 amps, which is actually a very typical current. Okay, part C, again, no calculation required. The minimum force on that wire will be 0 when and if instead of perpendicular, the conductor was placed parallel to the magnetic field. Okay, another example, straight wire, 2 meters long, current towards the east, that gives us our direction. The local magnetic field at that place, again, very small, and it's north and horizontal. So it's not pointing up or down, it's just horizontally due north, okay? Calculate the magnitude and direction of the force on the conductor. So again, since the field is north and the current is east, the angle is 90 degrees. I haven't really done many questions like this, but you know, what if I said the current was headed 30 degrees east of north? Well, then we would have an angle, right? And I could have done that, but in this case. So again, finding the magnitude then, just sub in the numbers. Pretty easy, it's in newtons. And then for direction, we use the left-hand rule. So it's current, right? So it's electron current, so we use the left hand, not the right hand. Fingers point with the magnetic field, which is north. Thumb foot goes east. So the direction of force will be straight down. Okay, and that's calculating magnetic force on a conductor, and that's it.